In this lecture we will develop the Y Combinator, which we have introduced as the medical solution to the problem of working with recursion on the basis of lambda and having let in scheme. So here it is. It's a combinator. It's another name for a function that does not have three names. It takes the parameter f, and in the function body we apply this function to itself. So there's a certain amount of self-application involved. This was the function that we introduced as a medical solution to our problems that we encountered in another video. So this is a scheme variant of the Y Combinator, but it may have several different forms in scheme. This one is a little bit closer to the classical legendary lambda calculus form here from above, and we can actually be a little bit closer but with this form, but as we will see, this is actually problematic in scheme. But enough with some loose explanation and hand waving. Our goal in this lecture is to develop this function step by step. Each step is primitive, and it can be explained rather easily. Let me warn you, there are quite a few steps, maybe more than strictly necessary, but I will take you through a journey from what we left in the earlier video, and it will end up with a Y Combinator. In an earlier video lecture we studied this expression. So we are trying to make the factorial function. We bind it to a name, and the factorial function calls itself recursively on a number which is one less than the original parameter. But this doesn't work. So we see here, we get the error that fac is undefined. And the reason is that the scope of this fac is the body of the let, whereas this name here is not within the scope of this name binding. It's easier to see if we rewrite the let to the underlying lambda notation, because here we have the name fac, and the scope of fac is here, but the formal parameter bound to fac in the outer lambda expression does not know what fac is. So we get exactly the same result here, undefined identifier. So far so good. We ended up with a solution which included the magic of the Y Combinator. So it's some function defined here. It's called y, bound to the value of this expression. And if we pass the factorial function, more or less at least, through the Y Combinator and bind this to recursive factorial, then we can apply this transformed factorial function to 5, and we get the result that we expect. So let me run this program, and I get 120. The goal in this video is to develop the Y Combinator. So we will show how we can obtain this strange function. We made the observation in the earlier lecture that the key to the solution is self-parsing. So this variant of my expression will work. I get the right result, but the punishment is rather severe because we introduce an extra parameter, f, and we pass fac to itself. So it also means that in the recursive call here, we must pass f to itself. So by passing a function to itself, we have it available in the body through the name f. But it should happen all the way through the recursion, and that's the reason it is rather unattractive for us as a practical solution. But this is our starting point, and the next step is to query this function here. So in isolation, we have this function. It's a 2-parameter function. Now we will query it, and this will give us this equivalent expression. So now we have lambda f, lambda n, and we have this calling form instead of the previous one because of the currying. Let us evaluate this expression again and see that we get 120 as previously. The next step would be to move this self-application stuff out of the expression for the factorial function stuff. So it can be done in several ways, but I choose to do it in this way. I introduce a let form where I bind g to this lambda expression, which has h as parameter, and I pass the result of f applied to itself into h. So here we have the parameter h, and in the previous version we had ff. I have switched to a one-line version of the factorial formula here in order to be a little bit more compact. Now we have this form, and let us evaluate it to see that it still works. We still get the same results. We are still safe. The next step is completely trivial. I decide to get rid of this name and call it something else because I don't want to confuse myself and others, so I call it I instead of fec. The next observation is that n is a free name in this expression because n is applied but not bound here. I want to pass it in as a parameter side by side with h. So this can be done in this way. So now an extra parameter here. So it also means that we need to pass it here. So now n is a bound name occurrence in this form. Again, no harm has been done. We still get the same result. The next step is to query this function here. It's a function of 2 parameters, and we can query it as we did before, so it's relatively trivial to do so. The function g, which is bound in this let construct, is now self-contained. It has no free names, and therefore we can actually move it out to the outer level. And we do this in this step here. So now we see g out here, and we apply g because now g is a free name in this expression bound to this lambda expression. So let's see if this transformation has changed anything. No, we still get the same result in our read-eval print loop. The next step is entirely trivial. We want, of course, to get rid of this empty let construct here. So here we are. We observed that now g is a free name in this construct, but we want to change this, and we want actually to pass it by introducing a new lambda form. So it is here, the new lambda form, and here we pass g as a parameter into it, and we apply j here, the formal parameter, instead of d directly as we did before. So again, with a clean REPL, does this work? Yes, still successful. We still get the result that we previously got. Now I'm a little bit tired of the location of 5 here. I want to move it out of this context. And the way to do that is to introduce yet another function call level here. And now we pass 5 directly to this thing here. And if we look carefully, we see that we actually return the result of I applied to itself out of this function, and 5 is therefore passed as parameter to I applied to I, exactly as we did here before. So it's a rewriting step which has not changed the meaning of anything, and let's check it. We still get the same result. Now we are actually close to our goal, because this is quite close to the Y Combinator, and what we have up here is actually more or less the factorial function. Now we again want to move the interesting stuff up top, so I want to move the upcoming Y Combinator out to the outer context. So we take this step here. I bound Y to what was inside before, and it has no free name, so we could do this, and we apply Y to G because this was actually what happened at this level. So now we are left with this form, and let us control it the usual way, still getting the right result. This is more or less the culmination of our work through a number of relatively simple steps. Each of them preserved the meaning of the program. We have obtained the Y Combinator here, and we use it down here. Let me do a little bit of rewriting to make things a bit more clear. So the next thing we do is to apply Y directly to the lambda function here, instead of having G bound to something and apply Y to G. So this is a very, very simple step we take here. And we could take another one where we pass the factorial function through Y, and we bind the result of this to fac. This is the recursive factorial function, and we apply it here. And it still works. If we want to go beyond as one simple expression, we can of course define a function Y here with define, with top level define, and have the same expression here. So, but now we have a defined form and a let form, but it still works. Many people are interested in the Y Combinator because this form turns out to be the fixed point of fac. So in practical terms we can demonstrate this, because this form here is equivalent with this form. If we apply fac yet another time to YFX, we get the same thing, and we can see that here. Still get the same result. We can do it yet another time and still get the same result, and so on and so forth. So that's the practical demonstration of the fixed point property. Now I want to work a bit on the Y Combinator itself. So I will take this lambda expression and substitute it directly for the two occurrences of I here, and that will give me more or less this form. I also change the names of formal parameters a bit, alpha conversions, so it gives me this nice form of the Y function. And the best of all, in a clean rebel, it still works. I will be tempted to do yet another thing. So if we take this form here, we can be tempted to eta reduce it. So get rid of the outer lambda and substitute the whole thing here with the body. That's doable. So let's see what happens if we go in that direction. So it's a rather pleasant simplification we are doing here. And we can define Y, and now we can hope that this still works. We've done simple steps many times, and this is another simple step. But when I evaluate this expression, nothing happens. So this was actually one bridge too far. It does not work in Scheme. The problem is that the lambda levels that we got rid of plays a role in Scheme because Scheme is applicative. Had it been a lazy, normal order reduction system, we could get away with this. But in Scheme, when we evaluate this, we enter an infinite loop, which will just go on forever. Whereas having this lambda level here will prevent this from happening. So there are some pragmatic things going on here in relation to evaluation order and applicative order. Now I'm in trouble here because I lost control of my rebel, so I will kill it and I will restart it. And I do that in that way, so I have a fresh one. Don't try it again, but I will actually try to play with this one, where I have done the eta reduction here, but not in this one. So let's define y, and let's evaluate this one, and this actually works in Scheme. So now we have shown how to develop the y combinator or the y function step by step. This one was a little bit too far, but we came up with this variant in Scheme. I should admit that it is relatively hard to grasp and explain the y combinator. But I have seen one possible way to do it. It says that y is a function that applies self-application to the application of f to self-application. Let me remind you that we throughout this video lecture have illustrated how to reason about a functional program. So all the steps we have taken is based on the fact that we can reason about a program, we can rewrite it from one form to another. We have used the rewrite rules, the alpha, beta and eta rules, which we will illustrate in the lecture about evaluation order. And we have used the principle of referential transparency throughout the rewriting steps. Moreover, I want to credit Richard Gabriel for writing the short paper, The Why of Why. The steps that I have illustrated in this video are greatly inspired by the work by Richard Gabriel.